All right, this lecture is on kinetic energy. The quote for kinetic energy says the factor most ignored in discussing interstellar flight is the kinetic energy that must be invested in the ship to make tons of matter move at a substantial fraction of the speed of light. So when we talk about the conservation of energy and how much energy is required to get something like a spaceship up to a very, very quick speed, you'll see that the amount of energy is enormous. So the goals, we should understand the factors that affect kinetic energy and how you can calculate kinetic energy. And once again, how we can relate kinetic energy to work, power, and kinematic motion. Okay, the key thing is to be able to relate it back to everything we've learned so far. And finally, you should be able to relate kinetic energy to the law of conservation of energy. You'll see the law of conservation of energy will pop up in every single one of these types of energy that we talk about. So kinetic energy. Kinetic energy is the energy of movement. If an object is moving, it has kinetic energy. If an object is not moving, it does not have kinetic energy. It is affected by mass and velocity. Okay? The formula that you have on the star chart is Ke equals 1/2 mv squared, where Ke stands for kinetic energy, half is just a term, and then you have mass and velocity squared. It is important to realize that the squared term applies to the velocity only. So velocity has a much, much bigger impact on kinetic energy than does mass, but mass still is an important part. All right, this question says, sketch the shape of a mass versus kinetic energy graph. So remember, we start off with our equation. We have kinetic energy is equal to 1/2 the mass times the velocity squared. And when you were to look at this, you'd say, okay, I'm interested in mass and kinetic energy, so everything else goes away because we would treat it as a constant. It would have no effect. So we have kinetic energy is equal to mass. And you can even leave the 1/2 in there. It makes no difference in terms of the shape of the graph. Now, y equals x, and we should know from experience that a y equals x graph looks like this. Remember, this part of the graph has no physical meaning because you cannot have a negative mass. So really, your graph should look like the positive quadrant, where you just have a line going upwards with no negative values. This is example 7.3.2. It says a comet doubles its speed as it approaches the sun, but loses half of its mass as it melts away. How does its kinetic energy compare? So we have our original formula, which we have Ke equals 1/2 mass velocity squared. And what we're going to do is we're going to see what effect it has manipulating these variables on the overall kinetic energy. So it says a comet doubles its speed. Remember, speed's another term for velocity. So instead of having v, we are now going to have 2v, and we're going to square it. Okay? But it loses half of its mass. So we have 1/2 0.5 m. 0.5 m lets me know that I lost half of my mass. So now we need to look at this overall equation. We say, okay, I need to get it back to this form right here. In order to do that, I'm going to square this out, and I would get 4v squared. Here I would still have 0.5 m. I still need this half term to make it fit, so I have to deal with that. So this can't be involved in this because I need this half term to make this equation work. So 0.5 times 4 gives me a value of 2. And so what I have is 1/2 mv squared, but I have this extra 2 factor that I don't know what to do with. And that's because the kinetic energy is actually twice as much. So if you double the speed and cut the mass in half, realize that the kinetic energy of the comet is still much greater. So a comet that's going to hit the Earth, if all things being equal, you'd rather it move much slower than necessarily affect the mass. Now the problem is that comets tend to move pretty fast no matter what, so the larger the comet would be more devastating. But overall, if you could increase the mass of it somehow, but somehow slow it down, that would make it more of a possibility that you could survive a comet impact. This question says calculate the kinetic energy of an 18 kilogram object moving at 20 meters per second, something like a cannonball. So we have something that is 18 kilograms and it's moving at 20 meters per second. Remember, the fact that it is moving is the key thing in having kinetic energy. So we can say, all right, we are looking for kinetic energy. Kinetic energy is equal to 1/2 the mass velocity squared. And now we can start to assign these variables. We said the mass is 18 kilograms, the velocity is 20 meters per second. So we can say KE equals 1/2 of 18 times 20 squared. So at this point we get our calculator out. We'd say 0.5, which is 1/2, times 18 times 20 squared. When we do that, we get a kinetic energy of 3,600 joules. A lot of people get stuck here and they want to make sure that the units match up because we've done that several times. So remember, kinetic energy, like any energy, is measured in joules or kilogram meters squared per second squared. So now when we look at the formula, 1/2 doesn't have a unit, but kilograms is the unit of mass, and we have velocity, which is meters per second, which we then square. Whenever you square something, it squares the top and the bottom in terms of the parentheses. So we have kilogram meter squared per second squared, kilogram meter squared per second squared. This question says calculate the velocity of an object with a mass of 50 kilograms and a kinetic energy of 10,000 joules. So 50 kilograms is pretty big, it's like 100 pounds, but we want to figure out how fast it has to move in order for it to have a kinetic energy of 10,000. So KE equals 1/2 mv squared. Okay, so we can assign these things variables now. We said the kinetic energy of the object is 10,000 joules. We can say that the mass of the object is 50 kilograms. And then we can say KE equals 1/2 mv squared. To isolate this v term, what I need to do is I need to multiply both sides by 2 over m. M cancels with m. 2 cancels with 1/2. So what I have is 2KE over m equals v squared. Take the square root of both sides, and what I get is the velocity is equal to the square root of 2KE over m. Now remember, whenever you do this, you have to do everything first and then take the square root at the end. That's what this indicates. So what I would say is I'd say 2 times 10,000 divided by 50, and whatever I get with that, I'll take the square root of. So we go to our calculator, we say, okay, 2 times 10,000 divided by 50. We take the square root of that, and we get a velocity of 20 meters per second. All right, so work energy. So one of the things we wanted to do is we want to relate kinetic energy back to work. And so we have what's called the work energy theorem, which is the change in kinetic energy is equal to the work done on an object. And this makes a lot of sense if you think about it when you're stopped at a stoplight in a car. What you want to do is you step on the gas pedal. And when you step on the gas pedal, your engine starts to apply a force to the car. And you apply that force for a certain distance. It could be, 100 feet, 200 feet, 300 feet, something along those lines. So you have a work that occurs. You have a force that's applied over a certain distance. And as a result of that force being applied over a certain distance, you have a change in kinetic energy. If we were initially at rest, this term would be 0, and we would have a final kinetic energy. But it's very important that you realize that kinetic energy and work are directly related to one another and can be calculated as such. If you look at the formulas, if you were to take these two formulas, you would also see some similarities between one of the kinematics motion equations and what you'll see here with work energy theory.
Okay, this example gives us a lot of information. So what I want to do is I want to start just by identifying the given information in this question. It says an object is initially at rest. Okay, well that tells me the initial velocity of the object is 0. It says is pushed with a force of 1,000 newtons, a distance of 15 meters. What is the mass? Okay, so I'm trying to figure out what mass is. And it says if the object reaches a final speed, final velocity, of 10 meters per second. So that's a lot of information that seems to be somewhat disconnected. Now, realize that we're probably talking about something along terms of conservation of energy. And why you can kind of start to recognize that is you realize that you have force and distance. Force and distance is what we learned about, which was work. We also have velocity, and we're trying to solve for mass. So what we're going to use is we're going to use the work-energy theorem, which is just another example of conservation of energy. And we're going to say that work is equal to delta KE, or the more useful term for us is going to be FD is equal to 1/2 m Vf squared minus Vi squared. So now, we can go ahead and plug our numbers in. We can say, well, let's rearrange and solve for m. So you're going to have Fd multiplied by 2 to get rid of the half, divided by Vf squared minus Vi squared. That is equal to the mass. So, when you do this, you have F times D is 15 times 1,000 divided by, oh, forgot our 2 factor, divided by 10 squared minus 0 squared. So, we go ahead and go to our calculator and we say 2 times 15 times 1,000 divided by 100, or excuse me, 10 squared is 100 minus 0 is going to be 100, and we end up with a mass value of 300 kilograms. Now I did want to show you that this work-energy theorem actually has origins in something else. We learned earlier this year, we said that Vf squared minus Vi squared over 2d is what? We learned that that was a formula for acceleration. Well, if you look, I have 2d over Vf squared minus Vi squared. So basically what I did is I took this whole thing and I did 1 over that. And I took this whole thing and I did 1 over that. And in doing this, really what I have here is F divided by A equals m, which is another example of Newton's second law. So if you realize what we're talking about in terms of energy, force, motion, they are all related to each other by these equations. They look like seemingly different equations, but you can get them multiple ways using the formulas you've already learned. Alright, this question says determine the force, so we know we're looking for F, that is required to accelerate a 10 kilogram mass from rest to 10 meters per second over the course of 100 meters. Now, we actually did some very similar questions to this when we were talking about dynamics. So you can actually solve this multiple ways. You can actually say, okay, well, I've got F and I've got M, and I can solve for A, and once I have A, I've got VI, I've got VF, and I can figure it out from there. But you can actually do it all in one step, and by doing that you can use the work-energy theorem, which says work is equal to the change in kinetic energy, or force times distance is equal to 1/2 of m Vf squared minus Vi squared. So we actually have the mass this time, so we can say that the mass is 10 kilograms. We can say that the initial velocity is 0. We can say that the final velocity is 10 meters per second. And we can also say that we have a distance of 100 meters. So when we look at this, we can say we are trying to solve for the force. So what I'm going to do is I'm going to take this D, I'm going to move it to the other side. In moving it to the other side, I actually have to divide both sides by D. So what I'm going to end up with is M VF squared minus VI squared over 2D. Okay, once again, you should recognize this right here. We learned before is VF squared minus VI squared over 2D is really A, or the acceleration. So, but for now we have it all in one step, and we can say that F is equal to 10 squared minus 0 squared over 100. So we have 10 times 10 squared minus 0 squared, so this is just 100 minus 0. 100 times 10 is 1,000. 1,000 divided by 100 is 10, and then 10 divided by 2 would be 5. If you're not comfortable with that mental math, we can go ahead and plug it into the calculator. We can say 10 times 10 squared divided by 2 times 100. And we get 5 newtons. Now, once you realize this, this is the exact same thing that we talked about before. You could use Newton's laws, Newton's second law, F equals ma, and the kinematics formula equation, A equals Vf squared minus Vi squared over 2d. There's multiple ways to solve these problems. So although I'm trying to show you the one that's relevant towards conservation of energy, any solution that works for stuff that we have covered will work.
So now you should understand the factors that affect kinetic energy. Number one is mass, and it is not a huge factor that affects kinetic energy, but it is a direct one. If you double the mass, you double the kinetic energy. However, velocity has a much, much bigger impact on kinetic energy. If you double the velocity, you quadruple the kinetic energy. If you half the kinetic or half the velocity, you take 1/4 as much as kinetic energy. You should be able to use the formula Ke equals 1/2 mv squared, and you should be able to calculate for any of those terms, kinetic energy, mass, or velocity. You should also be able to relate kinetic energy to work and power. Okay, we related specifically to work when we talked about, work, energy theorem. But you should also be able to take kinetic energy, and you should be able to use the kinetic energy to figure out what the power is by taking just energy divided by time. And finally, you should be able to relate this to the law of conservation of energy and saying, hey, if I have kinetic energy or I gain kinetic energy somehow, that energy had to come from somewhere. Work being done on an object, some sort of electrical infusion of energy. There's got to be some place that energy comes from.